what does it mean actually to solve an equation? Well, for example, where do the lines y equals x and y equals minus x meet? Answer, where they meet. That's one answer. It's kind of a bad answer. It's true, so that's good. But it's not what we mean by solving the equations, right? So better is to give the explicit point where they meet. Now that's obviously not a satisfactory answer in part 1, but in a more complicated example there will be answers partway between these two, which, for example, maybe eliminate some of the variables in the question, but not all of them, or not as many as you could eliminate. So it's worth thinking about why this is a bad answer. Well, it's bad because it's just restating the question, but, well, what's wrong with that? Why do we need more than just giving these two lines? There's more content to saying where they meet than just giving the definition of the two lines. You can be more explicit about it. Okay, so let's dig into this a bit. So first, I want to not stick with this description of lines. I want to be a bit more explicit. So when we say the line y equals x, the thing that's wrong with this expression is that it's kind of mixing up the idea of an equation and the idea of a function. Right? So we're used to writing down expressions like this to describe a function or its graph or maybe the equation that defines it. But I want to switch to thinking about equations and their solutions. Alright, well, so the line y equals x is the set of solutions of the equation y equals x. Or more precisely again, the set of all pairs. I mean, what's a solution? A solution is a pair of real numbers, one for each variable that could be substituted for in my equation, in this case 2, such that substituting a for x, which I'll write like this in the sort of programmer notation, and b for y, makes y equals x true. Okay, substitute a for x. Alright, so in set notation, and this is kind of just an excuse to give a brief rundown on this notation, Kenneth's going to do a bit more on set theory and so on in the next installment of the pre-course. So I substitute b, which is a real number, for y, which is a variable, and a for x, then I get the equation on the right-hand side here. And the way to read this notation, if you haven't seen this for a while, is the curly brackets you read as the set of, the bar you read as such that, and then the stuff on the right-hand side of the bar is some condition, which is either true or false for every thing that's taken from this set. So in this case we take all pairs where both coordinates are equal. That's the first line, the set of solutions of the equation y equals x. And similarly, L prime is the set of solutions of the other equation, y equals minus x. So So to rephrase the original question, to find where the lines meet, is to kind of compute, whatever that means, the intersection. So this notation is intersection. You take all the elements that are jointly in both sets. So if I take all pairs where both conditions are true, that's that. Now that's also not answering the question, just writing down this expression, right? There's 2 seconds thought that if A is equal to B and B is equal to minus A, then A will have to be equal to minus A, so A has to be 0. Back substituting gives B is 0. So we end up with our answer. Okay, so that's computing the intersection. All right. Now what I want to get to is a kind of general or more general algorithm for solving a pair of linear equations in 2 variables. And I'm going to stick with this example because it's simple enough to illustrate some slight switch in perspective now, which, as I said, is from equations that look like y equals x to just having polynomials, in this case, say x minus y. All right, so I'm going to, let's say, those were the lines I started with. I'm just going to subtract y from both sides and get x minus y equals 0. And, well, yeah, I'll add x to both sides in this one. No point having 2 minus signs. Although we often write down things like y equals x, it's actually kind of nonsense to write this down. Like what kind of equation is that? What are the things involved in that? So what we mean by writing down some expression like y equals x is either a function, meaning you can put in a value for x and get a value for y, or we mean a set of solutions of an equation or a polynomial, but this expression here is just false. It's in some sense nonsense. X minus y is a polynomial. It's not the 0 polynomial. So this equals here is kind of sus in some sense. So I want us to move away from writing down something like this and to think about instead just the polynomial, the thing that's going to be 0 potentially. Okay, so this is better to just take the thing on the left-hand side. So that's a polynomial. It's an expression in some variables. I mean, what you mean when you write this down is that it's kind of an expression which may or may not be true based on what you substitute for x and y, right? So it's potentially true or false depending on the particular values that x and y take. But we're going to switch to thinking about polynomials which are potentially 0 or not, depending on what substitutions you make. So if I make a substitution for particular a and b in R, then I get on the left-hand side a real number, which could be 0 or not, and I get on the left-hand side a real number, which could be a 0 or not. So this is true or false. So although this is pretty simple, there's quite a lot going on if you really think about it. So there are 4 letters that appear here, right? A, B, X, and Y. A and B, they're also not, they're not like 2 or 3, they're not particular real numbers, so they're in some sense variables, but we like to think about them as being particular real numbers. X and Y, on the other hand, genuinely are to be thought of as formal variables. the distinction between A and B and X and Y, I admit at this level of discussion is not completely clear. One has to spell out somehow a little bit more logic in order for the content here to be apparent. But maybe the best way to think about it is to say where they live. So A and B live in the set of real numbers, whereas X and Y live in the set of all polynomials, which we'll discuss later, but that's the notation for that. So this is the set of all polynomials with real coefficients. All right. So given those two polynomials, for any a and b, we can make the substitutions. We get statements that are either true or false. It's never true that x minus y is equal to 0, interpreting x minus y as a polynomial, which is why we've switched away from this and sort of disaggregated it into this entire story here. All right. So the question of where do the lines L and L prime meet is now the question of which substitutions of A for X and B for Y. So I'm going to write for the remainder, well actually it'll be more general in a second, but for now f1 is going to be x minus y and f2 is x plus y, these polynomials. So the question is, when I make these substitutions, which particular a and b make f1 and f2 both 0? So we write the result of substituting a for x and b for y in a particular polynomial f1, say, as f1ab. Right? So there is a distinction between polynomials and functions. The polynomial f1 is just this formal expression, x minus y. What I mean by formal expression can be spelled out, but I won't do it right now. But it's this kind of pattern of coefficients that I've indicated on the board, right? There's a 1 here secretly, and there's a 1 here secretly, and there's no x times y here, so there's a 0 there secretly, and so on. So the polynomial is this pattern of coefficients, as distinct from the function which it computes. So by making substitutions, I can define a function from my polynomial f1, but sometimes it's useful to distinguish between a polynomial, which is the formal expression, and the function it computes, and I want to do that here. So the polynomial itself is just the information of the coefficients. It's this very finite thing. All right. If f1ab is 0, we say ab is a solution of f1. And sometimes, you'll say, or a 0. In one variable, you might call it a root, etc. But we'll stick with solution here. Notice we can generate new polynomials from old ones. by taking linear combinations. So what we're working towards here is a general method for solving equations that are more complicated than the one we have on the board. And the way we're going to do that is by taking the equations that we already have and generating new ones. So if lambda and mu are real numbers, and I take lambda f1 plus mu f2, so now I'm doing algebra with these polynomials, right? And the way that works is just by expanding brackets and collecting coefficients. So that's lambda x minus lambda y plus mu x plus mu y. And if I collect coefficients on the x, that's lambda plus mu x plus mu minus lambda y. That's a new polynomial. Now notice something. If I substitute a for x and b for y, and this new polynomial, right, so I'm going to reach in here and put a, and I'm going to put b in here. Well, I might have just as well put a in here and b, and a for the other x and b for the other y. Or I might as well just have done it here, right? Put a and b in that polynomial and a and b in that polynomial. But we know that has to give 0. So if I call this f3, then evaluating f3 at ab, well, that's just going to be the same as evaluating f1 at ab, multiplying by lambda, evaluating f2 at ab, multiplying by mu, and adding them together, and that's 0. Okay, so whenever we take a linear combination, and linear combination just means take a scalar times one thing plus a scalar times the other thing in some collection that's fixed at the beginning. If we take a linear combination of the polynomials we have, our solution, AB, yeah, I guess I didn't say that. I'm assuming AB is a solution of f1 and f2. So if supposing we have a solution of both f1 and f2, and we form a new polynomial by taking a linear combination of them, any solution we had to f1 and f2 will now be a solution of f3. Okay, so we're going to generate first new equations. So let's maybe iterate here. I'm writing on the previous board. Just to be explicit. So we think about polynomials as standing for these equations. Right? So the equation x minus y equals 0, we think of the polynomial x minus y as standing for that equation. All right? So polynomials stand for equations. So you can think about f3 as being a linear combination of those two equations. All right, so if we have equations we want to understand, in this case f1, f2, we can first generate new equations by taking linear combinations of them, and then hope to have that be an easier problem. Okay, so I'm going to walk over to the next set of boards now. Please follow me. Okay, so example. If I take lambda and mu to both be 1, then f3, which is therefore f1 plus f2, is just 2x. And if I take lambda to be minus 1 and mu to be 1, then f3 is, what did I say? f2 minus f1. So maybe it's worth rewriting it here. So f2 minus f1 is just 2y. Obviously that's an easier system to solve, right? Okay, and there's something like a what we sometimes call a commutative square. If I take my original set of equations, f1 and f2, so let me call maybe this f3 and I'll call this f4. So I took linear combinations to get f3 and f4. Now it's an important observation that these substitutions, you can sort of do them either before or after you take linear combinations, and this was the point I was making by substituting a and b in the equation on the previous board. So the point I want to make here is the following. If I start with these polynomials, and then I substitute, I get some equations that are either true or false for each particular substituting real number a and b. Any particular linear combination I want to take of f1 and f2, right? So imagine a particular lambda and mu. I can make that substitution, I can take that linear combination either before or after taking the substitution. And as long as the algebraic rules that I use to manipulate polynomials in some sense mirror the algebraic rules that govern real numbers, then it's the same to substitute and then take the linear combinations as it is to take the linear combinations and then substitute. In more fancy language we say that making the substitution is a homomorphism of algebras. That's the same content, it just says that taking substitutions kind of preserves the algebraic structure which is involved in taking these linear combinations. Well, what's the point of that? Well, it means that so if I have a particular a and b, so taking linear combinations preserves solutions, I guess is one way of saying it, right? Suppose I find an a and b which make these 0, that is a solution of f1 and f2. So those will be true, right? If a and b are solutions, well, ab is a solution of f1, f2, then these equations will be true. And any linear combination of 0 gives you 0. So whatever linear combinations I'm taking to get f3 and f4, if I apply them to the left-hand side, which is 0, and the left-hand side, which is 0, I must get 0. So the resulting equations will still be 0. So these things, whatever they are, in this case 2a and 2b, will have to be 0. But since I can go either way around this little diagram and get the same set of equations, that means that it's also true that taking the linear combination of the equations will result in some new equations, f3 and f4, in which if I make the substitutions I get true equations. So if AB is a solution of f1, f2, it must also be a solution of f3, f4. Okay, so that's a little sketch of the proof of the following statement. I'll introduce some notation first, which will also be in the course proper. So let F1, F2... I actually think explaining that is much clearer if I introduce what a homomorphism of algebras is, but I hope that was reasonable. So let F1 be and F2 be polynomials. Then V, sort of bold V, of F1, F2 is the set of all solutions of F1, F2. That is, it's the set of all pairs A and B, making both equations 0. So what I was getting at on the previous board is the following inclusion. If I take any linear combination, say F3, of two polynomials F1 and F2, if AB is a solution of F1, F2, then it's still a solution, or then it's also a solution, or still a solution, of F3. Right, so if F1 of AB is 0 and F2 of AB is 0, then F3 of AB has to be 0. Okay, so that's the inclusion. That's notation for the inclusion or the subset relation. So it just says that everything in the left-hand side also belongs to the right-hand side. Another way of saying that is that adding or subtracting equations which is how you can think about forming F3, does not decrease the set of solutions. Now, this is a point which it's often difficult to communicate to first-year students in calculus, in my experience, is that when you do operations on equations, you don't decrease the set of solutions, but you may increase it, right? As is clear from this example, because if I just took F3 on its own and not F4, then what I'm talking about would prove that the 0 set of F1, F2 is contained in the 0 set, or the set of solutions of F3. But of course, this is bigger, right? That's just all the things where x is equal to 0. So in particular, it contains 0, 10, and 0, 10 is not in the left-hand side. Okay, so now we're left with a bit of a conundrum, right? Because if we have some set of equations like this to solve, how do I know when I've preserved the set of solutions? What's the point of forming new equations in the first place? Well, we see in this example that adding and subtracting those two equations gives us a form of the solution which is immediate, right? F3 and F4 are easy to solve. They literally just tell us the x and y coordinate of the intersection. So we want to try and do that in general, but we have to be careful that when we form these new equations, which are hopefully easier to understand, we actually preserve the set of solutions. We don't, we'll never decrease it by what I've just said, but we may accidentally increase it unless we're careful. Okay, so what does being careful mean? And that's the next thing I want to talk about. But are there any questions so far? Right. Seems not.
I had a question for that V notation. What was it called again?
I didn't give it a name. It's
okay.
Yeah, I just called it the set of solutions.
Awesome. Thanks.
Yeah. But yeah, what that's got to do with V, I assume it's some German thing, but I don't actually know. Kenneth, do you know why it's a V? Vanishing, maybe?
Wait, I just thought that V always stood for variety. Is that not right?
Oh, variety. Yeah, that's probably right. Yeah. So it's probably V for variety. Well, you can think about it as V for vanishing. But yeah, so I should... The set of solutions... That's what the V stands for. We'll come back to that in the first lecture of the main course. Any other questions? Okay, so let me maybe be a little bit more formal about the method here. So the method of solving linear equations, and we'll see that actually this works much more generally, and in some sense that's the point of the entire course. Is to first transform the system of equations in multiple steps, potentially. So you start with, say, F1 and F2, and now F1 and F2 are meant to be thought of as being arbitrary, but you can keep in mind our example. So you take some polynomials, F1 and F2, you generate some new pair of equations, F1 prime and F2 prime, by taking linear combinations. So F1 prime and F2 prime are both linear combinations of F1 and F2. And then you do it again. You take F1 double prime, F2 double prime, which are linear combinations of F1 prime and F2 prime, and so on. And you hope, or by an algorithm, you guarantee that eventually you reach F1 and F2 such that the following two conditions are satisfied. So the first condition is invariance of the solution set. What you want is that during this process, the set of solutions, well, we know from what I just said that it can never decrease, but I actually want to solve the original set of equations, that is, know precisely its set of solutions. I don't want to know some bigger set, maybe that's not informative at all. So what I want is for there to be equalities all the way through each one of these transformations, so that the set of solutions is exactly the same at the end, so to speak, as at the beginning. And secondly, I want the final thing to be easy to solve. So this is easy to solve, whatever easy means. And, well, in our example, F1 was literally X and F2 was Y, so it's easy to solve that. It's just on its face telling you the answer. Okay. So that's the method. That's how we hope to solve a system of equations, with this idea of both having transformations and having the end result be somehow already solved, or kind of obviously solved, or easy to solve. Just to spell it out, in the example we've just discussed, we kind of did that already. So we had F1, we had F2. F1, the final result was F1 plus F2, that was 2x. F2 was F2 minus F1, that was 2y. Why were these solution sets the same? I actually didn't argue for that, right? We could see it because we already knew the answer. We knew that in both cases the answer was 0, 0, but how did we know this was true? In some sense we kind of cheated, right? we already knew that the 0 set of that was 0, and we could see obviously the 0 set of f1, f2 was 0, just to be clear, right? So if on a pair this vanishes, that means the first coordinate has to be 0, and if that vanishes, the second has to be 0, so that's the only joint solution of both f1, f2. But what is a reason for this equality that is sort of a more general observation? Well, we know one way, right? That inclusion is what I stated on the previous 2 boards ago. If AB is a solution of this, then it's a solution of F1, because F1 is a linear combination of F1 and F2. And it's a solution of F2 for the same reason. So that means that if AB is in the left-hand side, it's also in the right-hand side. Okay, so that inclusion is clear. But what is a general reason for the reverse inclusion? Can somebody suggest some general reason which tells us why this inclusion has to hold as well? Yeah, that's right. I just used the same observation. Because I can write F1 as, well, let's see, to get F1 from capital F1 and capital F2, I should just take a half F1 minus F2. And to get F2 from capital F1 and capital F2, I should take a half F1 plus F2. And then we can just run the logic in the reverse direction, right? If AB is a solution of F1, F2, then substituting on the right-hand side, I'll get F1 is 0, and similarly for F2. So I get this inclusion. Okay, and if I have the inclusion both ways, then the 2 sets have to be equal. Okay, so this reveals the general trick. If I want to make the kind of transformations that I outlined on this board here, and preserve the set of solutions, I want, in some sense, this to work in both directions. I want each line to be a linear combination of the one above and the one below. And then it'll work. So what I want to outline over the next 10 minutes or so is the condition, which is a simple way of checking that a given linear combination, so going from one line to the next in this algorithm, actually succeeds in the sense that the solution set is preserved. Alright, so we're going to move to the next set of boards. So this means that the easiest way to arrange invariance, that is, it doesn't change, the invariance of the solution set is, well, it's now an explosion of Greek letters, is for there to be alpha, beta, gamma, delta, lambda, mu, theta, omega in R with the following. Well, to go forward in our algorithm, we need f1 prime and f2 prime to be linear combinations of f1 and f2, so here they are. And this guarantees the sort of forward inclusion, if you like. The vanishing set of f1, f2 is contained in the vanishing set of f1 prime, f2 prime. And we also want the inclusion in the reverse direction. Sorry? Oh, it's looking at the wrong board. Yeah, thank you. And we also want the reverse. So we want f1 to be some linear combination of f1 prime and f2 prime, and f2 to be some linear combination of f1 prime and f2 prime. And that'll guarantee the inclusion in the other direction. Well, that's a bit of a chore to find those 8 real numbers, but as many of you will know, and some of you may have forgotten, what I have implicitly here is a pair of matrices. One matrix is alpha, beta, gamma, delta, and the other is lambda, mu, theta, omega. And the 2 equations I've written down say that those matrices must be inverse to one another. And in short, that means that the lambda, mu, theta, omega are uniquely determined by the alpha, beta, gamma, delta, and such lambda, mu, theta, omega only exist if some simple equation holds, or doesn't hold rather, for the alpha, beta, gamma, delta. So that's what I'm about to explain, but the upshot is that as soon as I write these down, there's a simple condition I can check, namely alpha, delta, minus beta gamma is not equal to 0. And as soon as that equation holds, I know that lambda, mu, theta, omega exist with this property, and I don't need to go and find them. I can if I want. And that gives me a simple check for each step in my algorithm. Right, so let me now recall how you would see that. Okay, so note just making the substitution for f1 prime, that the second set of equations gives me this. Collecting coefficients.
Like ones that like these, but instead the little wings like this on these. It's already in a circle.
Alright, so you'll recognize these. If you haven't seen matrix multiplication in a while, this is something you should probably go and brush up on. I won't recall how it works, except to say that these coefficients here are exactly the coefficients in the product of the matrices lambda, mu, theta, omega times the matrix alpha, beta, gamma, delta. Right, so for example, the first coefficient in that matrix product is lambda alpha plus mu gamma, and that's what we see here, right? So that's where matrix multiplication comes from, of course, is exactly what I just did, is substituting linear equations into one another and collecting coefficients. That's where the rule for matrix multiplication originates. Okay, so but we already know, I mean, if you look at f1 here and f1, f2 here, we can actually read off something from these equations. I mean, one way to say it is that f1 and f2 are linearly independent, and then I can read off some equality of coefficients. I don't want to, maybe I want to state it in a more down-to-earth way, though. So, suppose there exist real numbers a and b with f1ab non-zero and f2ab equal to 0. Well, substituting a and b into the first equation on the previous board, so the one for F1, I get F1AB is equal to lambda alpha plus mu gamma F1AB. The second term vanishes because F2AB is equal to 0. In the second equation, 0 is equal to F2AB is equal to theta alpha plus omega gamma F1AB. Since F1AB is non-zero, that gives me theta alpha plus omega gamma is equal to 0. All right. If I go through the other two equations and assume now that there exists A prime B prime with F1 of A prime B prime equal to 0 and F2 of A prime B prime non-zero, and these two conditions together say that F1 and F2 are linearly independent as functions. If you are familiar with that, you don't need to be. So that's what I'm sort of setting up here. And if I substitute into the equations again, what I end up with are the following two additional equations. Lambda beta plus mu delta is equal to 0, and theta beta plus omega delta is equal to 1. Alright, so what I've just computed in these four equations is that under those conditions, that AB and A prime B prime exist with the given properties, I have proven that lambda mu theta omega, this matrix, times alpha beta gamma delta is equal to 1, 0, 0, 1. Okay, so we've arrived at a given some condition on F1 and F2, which of course had to exist, right? Because I could have taken F1 and F2 to be literally the same polynomial, in which case the game I'm playing doesn't make a whole lot of sense. I'm not really solving two different, not solving the combination of two different equations. I'm just solving a single equation, which, the line, if I'm solving a line equal to 0, that's a different kind of thing. Okay. So what's the conclusion here? Well, the conclusion is that under the existence condition, maybe I'll give this a name. So these two conditions together I'm just going to call Li for linear independence. So under this condition Li on F1, F2, which I'll just assume from now on, provided the original transformation, that is the alpha, beta, gamma, delta transformation, which produces F1 prime and F2 prime, as long as that matrix is invertible, and remember that a matrix is invertible if and only if its determinant is non-zero, which is alpha, delta minus beta, gamma. Okay, so as long as that inverse exists, then I can solve the matrix equation here for the other matrix by multiplying on the right by the inverse matrix of alpha, beta, gamma, delta, and it'll give me the unique inverse transformation, which produces f1 and f2 from f1 prime and f2 prime. So this is just the formula for an inverse of a 2 by 2 matrix. So it exists, that's all I need. Alright, so what we've arrived at is that provided I have this Li condition originally, and you can check that if under the conditions I've set up here on the alpha, beta, gamma, delta, and f1, f2, the Li condition still holds for f1 and f2. Maybe that's an exercise. So exercise. Check that f1 prime and f2 prime are Li, provided that matrix alpha, beta, gamma, delta is invertible. That's what I need to go to the next step, right? So suppose this is non-zero. So if I have all of this, then, well, since f1, f2 can be obtained as linear combinations of f1 prime and f2 prime, that's what it means for this inverse transformation to exist and satisfy that equation of matrices underlined in red. Since f1 and f2 can be written as linear combinations of f1 prime and f2 prime, I have the equality here. So my solution set does not strictly increase. Stays the same under that transformation. Okay, so that means I can continue playing the game, right? I can now take my f1 prime and f2 prime, define f1 double prime and f2 double prime as linear combinations of those, arrange for the coefficients in that expression to also have this condition, and then keep going, and hopefully until I find capital F1 and capital F2, which are a particularly simple form. And this, when you do it in a kind of more systematic way, is what's called Gaussian elimination, which many of you have seen before. I'm not going to recall the general algorithm, because maybe we'll come back to it when we've discussed Grosvenor bases and such. But that's what we'll learn is that maybe lying a bit behind this equality is that the ideals generated by f1 and f2 are equal. So that's something we'll come back to in the first or second lecture. Okay, now what I want to do is actually perform this series of reductions in a more interesting case. But before I do that, and that'll be the last thing I do today, are there any questions? All right. Let's see, how many boards am I going to need for this? More than one, that's for sure. Yeah, okay. Let's take a bit of a hike back to the place where we started. Sorry for those comfy on top of the rock.
They're all together now.
All right. So what I'm going to do now is have some more interesting lines than the y equals x and y equals minus x. And we'll see how, if there are parameters in my lines, the trick still works. and gives me an answer for the intersection point, which is expressed in terms of the parameters. And that's one way of thinking about what elimination theory is for. And that's the end point of the entire course, is to do something like this example, but in extreme generality. So here's the question. Where do the lines y equals m1x plus c1 and m2x plus c2 meet? Well, maybe they don't meet. I mean, if they're parallel, they won't meet. So if m1 is equal to m2, this question doesn't have an answer. But we'll come to that. This is not all lines, right? Because vertical lines can't be represented this way. So the more general thing would be to have something like n1x, or n1y rather, plus m1x plus c1 is equal to 0. And I invite you to do that as an exercise using the techniques that we're discussing here. Okay, but let's think about this problem. So where do these two lines meet? So maybe I'll give you a picture. So let's call this L2. And this is L1. So this here must be C1 and this here must be C2. This point P. Well, you kind of know that two lines that aren't parallel have to meet somewhere. Either because Euclid says that it's an axiom, or because you know how to do this and prove that such a point exists, or perhaps because you can name the point, right? Which you could do right now if you think about it. So while I'm talking, if you like, you can convince yourself you know how to write down P1 and P2 in terms of M1, C1, M2, and C2. It's not too difficult. But a priori, we don't know that it meets, especially if we're doing this in higher dimensions, or we have more complicated in higher dimensions and with more complicated linear equations. We don't necessarily know that a solution exists, but whether or not it exists falls out of the algorithm that we've discussed, suitably generalized. Okay, so the first step is to turn these equations into just polynomials, right? So our polynomials are, well, f1, just collecting things on one side, that's y minus m1x minus c1, and f2, y minus m2x minus c2. What we want, well, we want this to be as easy as the previous example. That is, we want to do this in one step. We want to choose alpha, beta, and gamma and delta such that, well, we're not going to have just x like we did in the previous example, or some multiple of x. It's going to be x minus some constant, but that's okay. So we want to choose alpha, beta, gamma, and delta such that this holds.
Now we have to figure it out.
For some P1, P2, we don't know what they are yet, and for some alpha, beta, gamma, and delta. And we want the condition of the previous discussion to be satisfied so that the solution sets are actually equal, so this actually solves our problem. Now if we can arrange for that, that is if we can find alpha, beta, gamma, and delta such that f1 prime and f2 prime, thus defined, do have this form for some P1 and P2, which are numbers, then by what we've said, the solution set of f1, f2 will be the solution set of f1 prime, f2 prime, and that's easy, right? The solution set of x minus p1 and y minus p2, what substitutions make both of those 0? Well, it's exactly x equals p1 and y equals p2, or a equals p1 and b equals p2 in my earlier notation. Right? So that will realize both of those kind of conditions in my algorithm, right? Firstly, that the transformation leaves the solution set unchanged, and secondly, that the final thing, so this would be like f1 and f2, the final thing is easy. Well, when we want something, the best strategy is to suppose it's true and figure out what has to be the case in order to make it true. So what I'm going to do is just assume that these equations hold, and then figure out what alpha, beta, gamma, and delta have to be. Okay, well, so we substitute, right? X minus P1 is equal to alpha times F1 plus beta times F2. And just expanding that out and collecting terms, I have the following. And that gives the following equations. Alpha plus beta has to be equal to 0. This is equality as polynomials. Right, remember I discussed, and we'll come back to what it means for two polynomials to be equal. It means that all the coefficients of the relevant things are equal. So on the right hand side I have something times y plus something times x plus a constant. And a polynomial is just a kind of list of the coefficients, and two lists are equal if and only if all their entries are equal. So for this equality here to hold, what I mean is that the left-hand side has exactly the same coefficients as the right-hand side, which leads me to compare the coefficient of y. Well, the left-hand side is, if you like, 0 times y plus this stuff. So I get alpha plus beta is 0. Alpha m1 plus beta m2 is equal to the coefficient, or minus the coefficient of x, and alpha c1 plus beta c2 is equal to p1. Okay, those are the three conditions alpha, beta, gamma, and delta would have to satisfy in order for this to work. And I get a similar set of equations from y minus p2 is equal to f2 prime. Okay, so from y minus p2 is equal to f2 prime. I'll just skip over the derivation, I think. So we get the equations I'm writing now. So let me put up here the first set of equations. That's alpha plus beta is equal to 0. Alpha m1 plus beta m2 is equal to minus 1. Alpha c1 plus beta c2 is equal to p1. And we have this condition as well. All right. So, let's solve all that. If m1 is not equal to m2, right, exercise, if they are equal, I mean, you know parallel lines don't meet, but prove it algebraically. So there is no solution if m1 is equal to m2. So suppose they're not. Then from, let's see, so from these two equations together, I can put beta is minus alpha in the second equation, and that will give me alpha m1 minus alpha m2 is minus 1. And therefore rearranging alpha is equal to this, provided the denominator is non-zero. That tells me beta as well. And then from the third equation I can solve for p1. Right? So p1 is equal to, well, alpha c1 minus alpha c2, which is alpha c1 minus c2. So therefore p1 must be c1 minus c2 on m2 minus m1. You should go back and look at the graph and think about why that was pretty reasonable. Right? Think about subtracting the two lines from one another and what the slope of that line would be. I mean, the point here is not to solve this in the most efficient way possible. We could have done that without any of the preparation. Right? The point is to illustrate this as a specific case of a general strategy for solving systems of equations. Okay, so we found the y point, the y coordinate of the intersection in terms of these parameters. And that's the thing I want you to focus on, is the role of the parameters in here and the fact that it's a generic solution. Now from the second column, substituting the first equation into the second, I get gamma m1 plus 1 minus gamma m2 is 0, and therefore rearranging gamma of m1 minus m2 is equal to minus m2, and therefore gamma is m2 on m2 minus m1. Substituting that into the third equation, I get this. Okay, so we're done. We've written the point of intersection as explicitly as it can be written. Now finally I have to check, in order for this to be sure that I have found the solution and the only solution, I need to check this condition that alpha, delta, minus beta, gamma is non-zero, but delta is 1 minus gamma, beta is minus alpha, so this is alpha minus alpha gamma plus alpha gamma, which is alpha, and that's 1 divided by m2 minus m1, right? So that's non-zero. Okay, so we're done. Right, we found the point of intersection. By that invertibility, it's the vanishing set of f1 prime, f2 prime, which is the point p1, p2. Okay, so the final point I want to make is that note our answer P1, P2 is written in terms of the parameters. M1, M2, C1, C2. So in this case, solving the pair of linear equations, to go back to the original question, right? What does it mean to solve a pair of linear equations? Maybe I'll get them back on the screen. So to solve that pair of linear equations, or what's the same, to find the intersection of those two lines, means in some sense to start with the original equations, which involve x and y, but mixed together, and to disentangle them in some way, right? And to find an expression for x and y which involves only the parameters. Now, as they appear on the board, they're all letters, right? Y and M and C and X. But we understand that the role of x and y is different to the role of M1, M2, C1, and C2. I can actually consider them all as variables in some polynomial ring and treat M1, M2, C1, C2 on the same footing as x and y. And in that case, what I'm doing here is pretty close to the kind of elimination theory that we'll be discussing at the very end of the course. So I'll return to this example with much more powerful tools later on. But for now, I think I'll stop there. Thanks, everyone. Are there any questions?